Okay. Okay, let's see. Everything seems to be doing good. Tell me if I have any issues with audio. Um, Stream looks to be healthy. Why that's having such issue? That will work better. So welcome to tonight. I'm sorry we started a little bit late. Um, Shouldn't be too much of an issue. Let's see. Otherwise, everything's looking good, looking good. So today, let's just go ahead and make this larger. Stick that in the middle of the screen. So we have an Aria 10 board. Sorry, my phone is not very well stabilized. Hopefully it doesn't bounce. So we have an Aria 10 board. That's a Goodell. Where's the name of this? Right here. Focus on it a little bit better. So we have a Goodell Hawkeye. Hawkeye 20G48. This is an Intel FPGA. We have an Aria 10 here. It looks like it's all that's under the heatsink, and this thing does get hot quite quickly. We have some debug ports. Unfortunately, the schematics and the overall usage of this device is not open, but we do have a few pins that we can work off of, so we'll see what we can figure out. I think there should be some example designs with at least the DDR pins or the other pins that we need to know about. Other than that, this Aria 10 board has 2 memory slots underneath the SODIMM. You see half of one here. There's another one about right here. And then we have a DDR4 SODIMM right here for a total, I'm not sure how many gigabytes is on this one. But this has 4 gigs, and this is probably, looking at the size, we'll have to look up the number of that, but probably 2 gigs. Can we look up that number? So that's an ANB47D9TGQ. We probably can look at how big that is. There's 2 of them. But yeah, so that should be a good amount of memory. So the Aria 10 board is compared kind of to the Zinc lineup. There is a hardcore processors on these boards. I don't know. If there's any what am I trying to say? I don't know how the processor works for this board. I have little experience. For the Zinc products, a certain amount of pins are dedicated to the processor, and a certain amount of pins are dedicated to the FPGA fabric. For the Aria 10, what I've seen so far, it looks like all the pins are part of the fabric. So maybe the processor is inside the fabric in a way, and you have to connect all the pins. We'll have to figure that out as we go. So today, there's a few LEDs. There's a D2 LED right here, and there's a D1 LED right here on the edge. And we're going to plug this into a PCIe slot. We're going to take one of the clocks, and we're going to do a counter, and we're going to see what we can get out of these system. Okay, so right here. So let's right there, refocus a little bit. Hopefully my typing doesn't clear that too much. So let's go put this back up into a corner. And we'll go look at Vertex 5 if we have time tonight. So we have a clock. And we're going to assign those LEDs based upon a signal. So I am so rusty in my usage of let's see, a VHDL unsigned counter, right? I'm just so rusty here. I always have to look at examples. Okay, so we have that. We have the hawk. We need a clock in, so we want a signal. Do a counter, and we get 32 bits. We're gonna make it unsigned so that we can do the fancy um, addition without much issue. Unsigned. I mean, you can do arithmetic onto the standard logic, but I've heard various opinions. Like you can add adds and subtracts to standard logic with some packages, but I've heard some unpopular opinions about those libraries. But that's okay. We'll just do this for now. So we have unsigned counter, and we want to do a process. Pretty easy. We're not gonna have a reset, so boom. It's gonna be on the clock edge event, so like that. And all we're really gonna do is say counter equals counter plus 1. I like using the pause edge thing. So I think we just say pause edge clock. Is that how we do it? Let me see. Pause edge VHDL clock. It's rising edge. That's what we want. Rising edge. Rising edge is the useful thing. It's very specific. You want to use rising edge. It's on a very specific transition because binary can actually have 4 different states. Or single bit can actually have 4 different states when you do simulation. And if you don't specify rising edge, other transitions from X to 1 or U to 1 can cause this. And we want to do rising edge, which is specifically a 0 to 1 transaction or transition. And then we'll go down here to the LEDs, right? We're just going to be LEDs. And we'll just say counter. We got to make these standard logic. We'll just say counter 29. We just say counter. Let's start at counter 27 and build up. Oh, we gotta make the standard logic. Can I do a controller? Nope, I can't do that. Can I do this? However, I don't like using this IDE. Do not like this IDE at the moment. Nope, do not like this IDE. Okay, that should work. We're just gonna do 1, 2, 3, 4. We'll assign the pins later. We're kind of guessing for the pins, but we'll see how that goes. 29, 30, and 31. It's 125 megahertz clock. Hopefully these tick at some point. But yeah, we'll see. Clock in, clock out. Seems relatively simple. Let's see what happens when we do synthesis analysis. Is there any log? Oh. Okay, cool. Did Andy forget how VHDL work? He may have. I've never been very good with syntax, no matter which language I use. Never been a good syntax. I also think it helps me not rely on one language, though. I can able to switch languages without relying on too heavy on this. I guess I just don't invest in syntax. When I switch languages so often, it's just not worth it to invest in syntax. Okay, I'm not sure. Let's go to a pin planner now and see if those pins show up. So we have these pins. We are going to remove those ones. Delete. Okay, node. Edit. Delete. Yes, we want to delete those pins. Yes, I am sure. Clock. Location. And I do A. We want to do AA12. I believe it's a pin. Clock input is an LVDS 23P. Seems like a valid pin. I'm not sure why it's red. So let's see. I have the other pins up over here, and we're just going to go through with the LEDs. So we have H23. H23. This is going to be E20. This is going to be H22, and this is going to be E20. And our last pin is status LED F17. F17. Yeah, maybe it's just the color. It must just be the color of the bank. Okay, so we're gonna save this. It looks like we can do fun pins here. Block pins. IO standard, reserve, off chip. Block pin. Okay, so I guess we save. We hit exit. And now we have those. Is that going to be in one of these? I guess so. Let's if we open pin planner again, I just want to verify that these pins are set. Okay. Now how do we chip planner? I'm an editor. I want to do clock constraints. How do I guess assignment editor? Attribute editor. Okay, so we need to figure out how to do clocking. Tools, timing analysis, chip planner. Okay, let's see. Fortis, clocking, timing analysis, quick study. Do we just do the timing analysis, I guess? Runs all filter stages. Specify clock constraints. Okay. So okay, we need to launch the timing analysis tool. I want to watch. Never use Quartus. This is interesting. So far, I like Xilinx better, but that's I'm sure that's a nice thing to say. I mean, it's just because did timing analysis fail? May have. Okay, let us go to plan at least, right? Did you not do filter? I guess that's part of filter. We shall do plan and then do timing analysis, right? Because I want to set a clock period, right? This is very straightforward on Xilinx's tools, but on these tools, I see no way to add a clock period to a signal. Partition planner. Ooh, got some cool tools. So, everything points at timing analysis. So we will do the plan first. I mean, maybe we can just add it. Like do an SDS file. Your files. We could totally add another file. Okay, now if I click this, see if anything pops up. Otherwise, that's a write it in to a file. Okay, we have this, right? Um, okay, teach me how to create a time netlist. No, it is not available. Um, clocks, report clocks. All reporting clocks. Okay, seems like there's no way here. So what we're gonna do is we're gonna create an STC file. So go here. We're going to say we're gonna do what, a new file. We're gonna do a constraint file. Is it that the file synopsis design constraint? Okay, we're gonna do a synopsis design constraint. Okay. Um, right. Let's see. And what is the period of 125 megahertz? Megahertz to nanoseconds. Um, Apparently this juggler does not exist. Period to frequency converter. Um, Frequency 100. Flip tool. 125, 123, 123 hertz. We'll say nanoseconds. 8 nanoseconds. Okay. So do an 8 here, and we'll do a 4 here. So we now have a constraint. We want to call it blocks. Save. The output files. Okay, so we now have a constraint file that hopefully is being referenced. Okay. So with this new addition, let us go to let us just straight up filter the thing and see how long this takes. And we get all the messages. Not initialize the timing now. Yes, we don't have any output constraints. Refer to the IO report for details. Oh, we have a error. Um, Argument targets. And we have a clock. That not period name clock. Um, That looks similar. Okay, try this again. Yeah, weird. Let me see if I can find any more examples. Hmm. Oh, we can fix that. Looks like we didn't assign the proper IO standard for the other ones. Some pins, there are 12 RX. Yeah, yeah. That is okay. Looks like that was better. Replace it. And routing. Hopefully this does not take too long. It should be relatively quick. That's good. So we need to go to the pins. Okay, so let's check out timing analysis now. Let's see if we get anything different. Okay, yeah, that's good. Um, um, do I just click one? How do I create one? Netlist create. This must be the create timing netlist thing. Um, let's see if there are any output constraints. Yes. Output delay constraints. Okay. To set output delay, repeat step 4 to 6. Okay, so let's go ahead and close this. Go to our SDC file right here. Why they deem that necessary. LED. We'll do some output constraints. Not that it really matters. Okay. Sure. That seems fine. And then let's go to our pin planner. These guys, their IO standard should be 3 volts. 3OV LED, LEVT. Can I like highlight more of them? Nope. This is really slow. Okay. So if we got anything else in the AF region? Looks like a Adlob SFP. What's the SFP? So I don't know why this one, I can't find that in the thing, but we're gonna put it. It should be, must be something to do with a pin. I guess it's LVDS. I don't know. It's a single signal. So LVDS is usually differential signals. I don't know. Type of signals we got here. AA12. Let's make sure I got the right signal to be. Oh, it's AA16. That is a read-only item. Well, filter location. AA16. Oh, so clock inputs. That's good. I wonder, I'm trying to figure out what constraint we should use for this, and it can be very important, so I don't know. Where are these reserve pins? Any place where the any other place where the IO standard is just AA12 is LVDS. Let's see, it's IO standard. IO. The IO standard. Yeah, 1.8 volts. Okay, so we're gonna call this as good. Sorry, what? That you missed some of that, but I think we're good. I wish I could show multiple monitors. I think it'd be cool if we could have a 3D setup. Maybe I'll stream 3D someday. Where you can look at my multiple monitors, like a head behind my shoulder VR. It'd be like cool to do a VR one. So okay, we have output delays. We fixed the pin delays. Yeah, let's go ahead and do all that again, and then we'll plug it in, turn this on, and program it, and see what happens. Oh, while we're doing this, let's see if we can look up this guy. So we want let's go here to the good old Google search. We want what we want 8NB 47. What happened to, why did it do that? You want 8NB 47 D9T GQ. What is this? Yes, this is micron memory. Ugh. There, let me start there. Come on. ANB47. That's all I got. Maybe just go to Micron and see if the product lookup has anything better. Micron. Products. DRAM modules. You think it is RLDM? UDIMs? I want to say UDIMs, but I don't know. See, the names are much different on these suckers. View product catalog. I don't know. Okay, how's this going? Ooh, let's do timing analysis sign off. Yeah, I'll have to figure out what parts these are. Very annoying that that value is not what they are. Oh, put that back. Successful. Generate programming list. Okay, let's get this thing hooked up and going. Okay, it's on. So we're gonna plug it in. See what happens. Okay. So it looks like it all went well. I didn't really do patent. I didn't do that one. So let's go to Mr. Programmer and program this guy. Program configuration. Okay. Hardware setup. There we go. YouTube. Yep. Close. SOF. Yeah, let's start this and see how long it takes to program and see what the LEDs do. And if this doesn't work, oh, I don't know what to go from here, man. That'd be rough. Okay, so we see the, oh, you guys don't see the progress. Let's see the progress right there. 6%. This is dramatically slower than Xilinx programming. That being said, I am not necessarily using a full price JTAG programmer for this. I just wanted one that was valid. But for it to take this long, it's kind of ridiculous. Maybe we can compress it. While we're doing this, I'm curious to see if there are settings. Do we have settings? Virus? No. This where I edit it? I am totally unimpressed. Here we go. This is useful. Restart, clears, enable autonomous user code configuration, generate compressed OS SOF. Allows you to so why can't I? Maybe I have to do one of these ones to do that. Okay, back to programmer. Back to programmer. We are at 55, 56. And just so we understand the time frame, so the quickest one is going to be 2 to the 28th. And we want to divide that by 125. What? Divide that by 100. 100, 25, 1, 2, 3, 1, 2, 3. Equals, so every 2 seconds, the lower light should go. And divide by 1, 2, 5, 2, 1, 2, 3. Every 34 seconds, the big light should toggle. So between 2 and 4 seconds for all the lights is good. We're at 66. It sits at 66 for like the longest time, and then it goes. And then we gotta do the Vertex one. That'll be fun. Okay. And this goes. Okay, successful. Oh, okay. We have progress. Let us look at this. I'm going to take my headphones off and show you the camera because we're kind of limited on space. Okay, so those two lights are working. That status lights. That status light isn't changing. So I'm not sure about that one. But if we look at the back of the board, have we have 2 LED locations. Seems to be a green and a red at each. So you have 4 different colors: blank, red, green, and orange. I don't see where the status LEDs come from. So yeah, there we go. We have properly programmed an Intel FPGA. We learned how to do it. Now we got to figure out the memory and PCIe. So look for future videos on more complicated systems. Okay, let's return back here real quick and talk about the Vertex 5. Vertex 5 is going to be fun. We're going to be using ISE, and it's going to be a nightmare. Okay, no, we're fine. Okay, we're gonna exit Quartus for now. That's an adventure for another time. I'm going to kill the Linux machine over there so we can swap out devices in a second, depending upon how long it takes to program those devices. Sudo shut down now. Okay. Give me 1 second. Gotta properly shut down, power down all this. Little test platform for my fun little stuff. Okay. Done with the Intel board for now. Okay. Now we're going to do the Vertex 5. And I see that my phone is directly in this video. That must have been annoying. Okay, let's talk about the Vertex 5 board. So this is whatever. Okay. So for the next 45 minutes, hopefully, we're going to be looking at the Vertex 5. This is the LTX 110. This is an AVNet board. Great because the schematics are open. I can grab them. We have PCIe, some expansion slots, QSFP ports, Ethernet. Is that USB? We have a USB-B port. Another Ethernet. Some. That's a fancy video thing, I think. FPGA. Expansion. You can power it through 4 pins, power it through this, or you can power it through PCIe. We're going to power it through over PCIe for now. Oh, it's got a SATA port. That's nice. The only damage I saw on this used board were these two buttons up here. But overall, I like it. I may resolder those buttons sometime later. Some new stuff. It seems like a pretty basic push button that I probably can find. Actually, let's look it up real quick, right? So if we go AES right here, this guy, this one, I want to look at what PB1 is. What is PB1? PB1 on. Okay. AVNet push switch replacement. I am not a robot, I promise, guys. I'll have to look this up another time. I wish they gave me the part here. They just got SFPST. And you're not gonna give me, if I put this right here, you're not gonna give me anything useful. 40,000 products. That's great. Analog switches. So yeah, if anyone knows what these switches are, make this a little bit bigger for now. You zoom in well. That light, let me that light. I'm looking for these type of switches. What is the focus and showing? These type of switches. Maybe but that's okay for now. It's a generic switch, doesn't control anything important. And if in all honesty, I probably still can deassert them. I had something pointy. Let's see. I don't feel anything. So yeah, it probably might be broken. But we have a lot more LEDs on this one. We have these LEDs, so we can make a fun one here. Okay, so let's get ISE up and rolling. So for ISE, Xilinx provides a virtual machine, a virtual box or VMware virtual machine image that we can use. So let me pop that open real quick. And we're going to start a new design. We're going to use the required FPGA. Oh. So what we want to do is we want to... I need to probably set up... Yeah, that's fine. Give me a second. I think I need to fix some network connections. To do... oh, get out of there. Let us go. Okay, cool. Now, so our FPGA part is the LX110 VFF1336. So okay, let's go create a new project. Boom, boom. Let's do what's it, Control F? Switch. Yeah, sure. So we're gonna open up Project Navigator and create a new project. Yay! Nothing like using ISE 14.7. Okay, we already got one there. So file, we're gonna do a new project. X up, yeah. Name, we're gonna call this V5, or let's call this AV5. We have an AV5 board. Next, we're gonna do Vertex 5. It's gonna be 110 T. Let's see. Is it 110 T? Okay. 110 T. And 1136. What is the speed grade? Good question. I had to assume the speed grade is high. We'll do that for now. 1136, right? Yeah. We'll assume a speed grade of 3 because of PCIe on it. It might be speed grade 2. I don't know. No one tells me. Let's see if there's any if we can discern the speed grade from pop or something right here. No speed grade. Do we have speed listed anywhere? That's the only place speeds is located. So we have no clue what this Vertex 5 is doing speed grade wise. But since we're using PCIe, I would assume a 2 or 7. Like, okay, let's do this Vertex 5 PCIe, right? Yeah, let's see. Let's see what's capable, right? Project description. I want to look at no, that's not what I want. I want the Xilinx. Is that it? Yeah, sure. Do 5 link. There should be like a speed grade product table, right? There's speed grade, speed 23. Yeah. I guess it doesn't matter what speed grade we have for PCIe. It should matter. Matter a lot. Let's do with -2. I guess that's probably the best we're gonna get. -1, -2. Three. Okay, yeah. PCIe and let's just type speed grade. Right here. Okay. Go to PCIe. Look at that. It's the same across the board. PCIe core, user clock core. So let's assume speed grade 2 then. Sheesh, I did not suspect that. VHDL, sure. Next, finish. So let's go ahead and copy what we did in our previous one. So we're gonna go ahead and do a new source. We're gonna do a VHDL module. We're gonna call it top. It's gonna have a clock, and it's gonna have LEDs, and they're gonna be a out, not an out, an out bus, and the most significant is gonna be 7. Sure. Finish. See, I love Xilinx. It's like, hey, do you want these things? I'm like, great, you did wonderful. Let's pull up let's just copy real quick the other ones. I'm gonna pull that up on a different monitor super quick. And we're just gonna copy over that system. Okay. But let's make this a little bit easier. We're gonna do LEDs. So we're gonna do a whole LEDs. But then we're gonna do 30, we're doing 31 down to 24. That should be the 8. That matches up. Okay. Now let's pick a clock. So we're gonna need to look at the schematic. Let's go find a clock. Where is a good, reliable clock? Hopefully a single pin clock. I want a single pin clock. Expansion switches. GMI, clock out. And we got differential clock in right there. DDR, clock out. DDR, compression. Got any good ref clocks here? I might have to look for refs. I got that board. I do. So let's see. We got any clocks? Let's see what clocks we got. Clock 100. There we go. Boom. Single-ended. Oh, we have our LEDs on this bank as well. So bank 3. We're gonna rely everything on bank 3. What is the what is the VCC for this bank? We got 3.3 there. Do we not have? I assume this is running off whatever the bank is running off. So probably 3.3 because flash A22 is going to 3.3 volts. All up. But yeah, where is the he's not listed well here. Oh, there's the mode pins. Okay. Okay. They did not do a good job of telling me the IO standards to use for this. Okay, we're going to assume this is all 3.3 LCVMOS or whatever, LCVMOS. Okay, so we're going to use H12 and then we have the other pins. Okay, so IO planning. Great timing straight. See, this is probably like it. Create. Okay, so we have something here. Yeah, let's create timing constraints. Sheesh. Oh yeah. This is a vector. In case anyone is running. Okay. Yes. So we're creating UFC. We're gonna create a constraint. Clock neck, TS clock, sure. Period. I think we can do this. Yeah, we can just say it's gonna be 100 megahertz. Yeah, create. Okay. And then outputs. Create a constraint. LEDs. Next. Clock output. Period. Yeah, sure. So there we go. We hit OK. So we save that. Now how do we exit the time? I just hit exit there. Oh, yes. Okay. A little bit confusing. Let's say LED underscore T. Okay, cool. Let's go here. Let's go to, yeah, post synthesis IO planning. No. Let's go ahead and close that guy and do this. Okay, cool. Plan ahead. Sourcing, initializing project. Cool. Let's go ahead and point out these pins and then do implement design and then see if we can program it. Use impact, good old impact. Okay, so we'll do the clock first. They're all gonna be fixed pins. The clock is H17. We useless. Ah! There we go. This guy right here. Scalar, clock, sites. I want H17. Boom. LVC MOS, yes. LVC MOS 33. Yeah, that's the one I want. Okay, all these LEDs. Okay. Let's go with what they say. LED 0 is H13. H13. And then we have LED 1 is J17. J17. 7. Sheesh, make it that way. Let me J21. 6 is J19. This one, 5 is H. H. There's other ways that you can totally write a constraint file. I'm just going the way of the GUI because I think this is a great example to see a GUI in action. And I know this is an older tool, and I don't know, it's a good experience to play around with the older tools in case you ever have a project or you find a cool used board and you're like, hey, I want to get this working. Okay, so these are all good. We're going to save it. It was saved to the constraint file. So now we should be able to close out of this. Plan ahead. Yes. Yes. Okay, so now we have different things. We now have ports and constraints. Okay, cool. Now we go to this guy and we implement design and we'll look at the timing report and other things. We'll have place and route. We'll look at the generate post static report. And yeah, I think that's about it. Oh, we have failed. Encountered a error. Errors. What errors did we get? Interesting. Let's go back to that schematic. So it's asking, what's it asking? It's asking, oh, that's why. I'm sorry. I don't know why that happened. Ah, silly me. Okay, yeah, let's go ahead and implement design again. Like that did not match. So, usually with an FPGA, you need to have your bank have the same I/O constraint. Or generic. So these are all in the same bank 3. They all need the general same I/O constraint. I need to figure out all these clocks. Maybe rough. So yeah, we got this SODIMM. 128 megabytes. It's gonna be that only page, which is like the last one. Dim. I'm trying to figure out what clock. Are there any good reference clocks for this? We have a CK in. So that's weird. So like that looks like an input, right? Or maybe it's just the way it's connected. Those arrows don't necessarily mean input. No, those are different. Okay. I'm not sure what the ref clock for this guy is. I have to go exploring of the different clocks. Because we have a dim clock feedback right here. And for the G ref clocks for DDR clock. Out. Have to look up that part. Yeah, we probably have to go look at how all the clocks are generated. I have to look at that part. Curious, right? What's this part? What does it do? Dual level translator. It's a dual voltage level translator. Oh, yeah. So let's go back to. Is there no guide for this guy? I got a schematic. That'll get me places. That's what we want. User guide. Net Vertex 5. Okay. in not what we want, but that, on the other hand, is. Woo! Found my guide. Okay. Explain to me how you plan to do PCIe connector. Great, great, great. Ooh, great information. Vertex 5. I love it when boards have useful information. I should save this immediately after. I want to look at the SODIMM, DDR, SDRAM. I don't really care about that one at the moment. We want to look at the SODIMM. To do. Okay, the extra pins are dedicated to a clock. It's populated. The bandwidth. The systems are connected to banks. The output supplies. What's a good reference clock? The bandwidth of the 5 speed grade module is forced with a memory clock. Oh, so we can support more. Okay, okay. Okay. Oh, no fancy picture. That's going to be a nightmare to figure out, right? Do. Okay. Oh yeah. What's a speed grade? Speed grade. Oh, I have speed grade 2. Lucky guess for me. Okay, cool. I think we're doing fine. So, place and route. Let's generate. Can we view it? Timing summary. 0 errors. Okay. So we're gonna generate the programming thing, and then we're gonna pull up. What was the tool? XSCT? Yeah, it might be a tool. It's been a while. Can we open up a new terminal? XSCT, CST, it's XMD, XMD. Bugger. Yeah, this one's way more complicated and annoying. Okay, cool. We won't worry about that. Close. Okay. Oh, did I close it? I closed the. Yeah, I had the other terminal. That's fine. It'll take a second to get back up and running. Okay. Okay. Um. Shouldn't take long. Oh, so nice. The tools run so fast. Vivado is so much more bloated than this. Okay. Okay, here comes the fun part. Getting this programming thing to work. So what we want to do is we're going to plug in the newer Digilant one and see that even shows up. But maybe we have to program it. Okay, cool. Did I get a message from someone? See a message. Okay. We have impact. I guess plug it in. Options. Been so long, guys. I don't know how we did this before. Okay. Devices, USB. We want to pass in. Yeah, look at it. It already has it. Boundary scan. Initialize chain. No cable connected. We may need a ls cd/opt. Been so long. Yeah. I think they don't have the SDK. Well, that is going to be annoying if I don't have the SDK. The SDK has to be in DK. Oh yeah, sure. We want to look at XICOM. It's data. XI. Nope. Cable. Yes, this is annoying. Do, 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 do. Do this, and we want to find dash name diligent. Go. Probably put a star before and after. Driver. Right there. I spelled it. Do cable connected. So we're gonna unplug the cable. We're going to go to CD. Yeah, we're just gonna go to ISE bin lin 4. No driver. Where is it? We're going to install. No, go here. Play. Can we have install? Okay, did I get lost? Bin lin64 install script. Should be here. Okay, so there's an install drivers. chmod plus x install drivers. Bash sudo dot install drivers. cd install scripts. ls cd install drivers. ls install drivers. ls Linux drivers. ls where was this Digilant one? Oh, we gotta go back up. cd dot dot slash dot dot slash dot dot slash right here. cd Digilant ls install drivers. Control C, sudo bang bang. So we successfully installed these drivers. Okay, cool. Now we're gonna plug in this guy. We want to see if cable is detected. Devices, USB. Okay. Let's go back here. ISC impact. Cable auto connect. Okay, cool. We're connected. We have the device. Okay, we're gonna go plug in the FPGA. Nope. Okay. Okay. So these LEDs can you so we're going to be looking at those LEDs. Okay, thank you for paying attention. So we're gonna do a boundary scan. We're gonna do we're gonna initialize chain. I don't know why this is suddenly so slow. Oh, the select program is being used by another application? Okay, give me a second real quick. I need to go and figure out why. Oh, sheesh. Let me go kill hardware server. Details. Hardware. HHH. Okay, it doesn't look like it's running. That's good. Now we're gonna say give it back. We're going to. Don't know why this is so slow at the moment. So table initialize chain. Oh, on the road. Table auto connect. Oh, nothing like freezing up your computer. Okay. Um, no cable connected. Um, auto detection failed. Let's try this again. So devices, USB. Go here. We type in the message fail. Okay, yeah, it was seen. Okay, let's go back here. I'm going to open this up again. And we're going to boundary scan. I will set connection failed. Okay, cable setup. I don't care. We're using a digital cable. Oh, do I need a sudo start this? Okay, let's see if we close this, impact. Let me open this. Oh, did I click something I wasn't supposed to? No, no, cancel. Boundary scan. Auto detect. Hmm. USBs. These settings. Um, Uh, okay. What's the best way to do this? Close that out. Unplug, plug it back in, and see. Oh, okay. That's VirtualBox broke. That works. Um, Settings, USB. Can we do that one? Start. Okay, so VirtualBox crashed. We're so close. Hopefully this works. So many things plugged in. Okay, so the first we're gonna do is we're gonna do a plug that in. Uh, Hang a terminal. The hotkey didn't work. The message tail. Um, um, okay, seems to have worked. So let's try it. Let this no. You want to yes. Cancel. Okay, boundary scan. Let's try this again. Auto connect. Booyah. Initialize chain. Booyah. Yes, I want to pick a configuration file. It's going to be in. Oh, wow, this is actually a shared folder. I did not realize that. I'm looking for AV5. AV5. Ooh, there we go. That should work. No. Okay. And then we're going to program. Look at this. Look how much faster this is. This is beautiful. And look at that. We programmed the LEDs. Yeah, we need to unplug the phone so we can look at it a little bit better. Yeah, which one? Right here. What we programmed on the ISC program and working great. We'll wait. Glass LED works. Close. Glass LED. Cool. So yeah, that is well it for the day. Thank you for joining us. So yeah, we saw an example of Cordis. We saw an example. I will power this down, take a quick picture, and post that as clickbait, I guess. Anyone really cares? Oh yeah. So we can program things. Any closing remarks? Tomorrow is game day. Thursday we will look at putting Ubuntu on the DCU 104, and Friday. I think Saturday morning we're gonna do programming. Friday we would want to look at doing a custom design. We'll see. For the Ubuntu, I want to figure out how to get Ubuntu working well. Okay. Maybe get wine working on it. That'd be fun. So that is all we have today. So we're going to go ahead and close this and just save the machine state. Okay, and so please join us for tomorrow or Thursday. I hope these sessions are entertaining and fun. I know I'm looking at getting a Discord channel later. maybe 1,000 subs or something like that. And then we can look at having some maybe active conversation during these things. Depending upon how popular it, we may need to I don't know, limit how many people can talk, and if there's people worth to ban, but might as well try and see where it goes.